Okay, so anyway, let me start. So welcome everyone. So I just started with a Python review. So as I said earlier, there's going to be 3 parts to this lecture. First part, quick Python review, it's 5 to 10 minutes. And then we're going to spend some time on feedforward neural networks just to get the terminology, the words used to describe various aspects of the model. And then we'll get to handling image data using convolutional neural networks. So that's the agenda for today. So as I was saying, so I just opened the Python review notebook. You can clone, you can get to this notebook by cloning the repository if you want, and then just going into the notebooks directory. So actually cd into the deep learning folder and the notebooks directory. And you'll see a bunch of notebooks. You can just open Python review. And then I was saying that, so this is a Jupyter notebook interface. And for those who have not seen it, and I'm just showing that there's a bunch of cells. You can execute cells by pressing Shift, I think Command Enter, sorry, on Mac, Control Enter on Windows. You can look at the help. So you can see keyboard shortcuts. There's a bunch of shortcuts. And I'm on Mac, so it's showing shortcuts relevant to Mac. It's worthwhile knowing how to use the shortcuts. So basics, a bunch of variable assignments and print statements. And these tricks you might have seen before, how to increment a variable, shorthands, and so on, but you don't have to use them. You can assign multiple variables at the same time. That's a comma b is equal to true comma false. Strings, we can use strings are assigned like this, and you can actually print everything at the same time. So and strings have functions that with which you can change the case and so on. Now, the most interesting objects that you'll probably work with, at least at the beginner level, is going to be a list, a tuple, and a dictionary. So let's look at a list. A list is a collection of elements. Tuple is also a collection of elements. The difference is that a tuple is immutable, whereas in the list, you can reassign elements. So this is how you would define a tuple, and this is how you define a list. And here I just changed the elements in the list. There were strings, I mean characters, but we can change we don't have to have the same type as elements in the list. So for example, in this my list, I appended the list with an additional element 5, and then extended this list with a different list, which is a list of 2 elements, 7 and 6. So you can see that the types of elements in this list are different. First 3 elements are of type character, and the last 3 are integers, and you can check that. As well as, I mean, so list indexing is also useful. So you put a colon and the element and the index of the element that you don't want. So basically, if you so list indexing is from 0. So if you don't want second element onwards, starting from the 0th element, then you can exclude that on and do a colon 2, for example. So it will just take the first 2 elements. And here I'm assigning the first 2 elements to be a comma a. And you can see that here it became a comma a instead of c comma b. So there's another data type, which is a set. It's useful if you want to, for example, find unique elements in the list. So if I do a set of this list, you can see that a has repeated thrice the character. And so if I do a set, then it just folds to 1. So these are extremely basic data types. Many of you might have seen this before. And as I said earlier, the third interesting data structure or data type is a dictionary. A dictionary is essentially a key value map. So you can index elements, the values. So you can index using the keys, and you can get the corresponding values. So here I created an empty dictionary, and I'm creating a key, and keys have to be immutable. So as I said, a tuple is immutable. So this tuple here, 576, is immutable. So you can use course of 576 as with a value of advanced prediction models, and you can have a different key. For example, 572 is data mining, and so when you print this dictionary, it just prints the keys and values, and you can iterate over. iterate over dictionaries as well, but here I'm showing the iteration over a list. So my list is not defined. Okay, I didn't run much of it. Let me just run this. Yeah. So if I iterate over the list, I can just do something with the elements of the list. And there are extensions that you will see, some programming patterns. Like, for example, if you want to iterate over a list, but you also want to get the index of the element in the list, and you can do enumerate. Enumerate so that you can get the index location and the values of the list themselves. I'm not going to show work using pandas, but pandas is a great library that you can try to get started with. For example, here, instead of having lists, you could have the 0 and 2 as index of a data frame, which is a concept that you might be familiar with from R. And for example, the characters could be in a column. So you could have column names, and you can do interesting slicing and dicing of that data frame. So next, let's look at functions. So here I have a function that we saw actually last time, which is the softmax function. So in the back propagation example last time, we were looking at a function which is 1 by 1 plus e to the power z, e to the power minus z. So this is that function. I just defined it here. So this is how you define functions: def, function name, input arguments. There could be, this is called a positional argument. You could have, you could have arguments that can be can have default values, and you can also have arguments which can move around. In the sense, you can flip their order, and it doesn't matter. And for this, I'm just importing the math module and the NumPy module. The NumPy is going to be very similar to PyTorch in terms of handling of our data, which is mostly going to be numbers. Last time we saw an image was essentially a width times a height times some depth, and the depth was like 3 different matrices, 1 matrix for each color, for example, and we'll see that today. So NumPy is very useful. So you can convert a list to a NumPy object by numpy.asArray or numpy.array as well, I think. So here we are applying the softmax operation, softmax function on a single variable. Okay, we can also apply it if we define it appropriately. Maybe this one will work, but we can also apply. Oh, yeah, okay. We can also apply it on a vector. So NumPy array here is actually a 1-dimensional array because there's only a single list here. If you had a list of lists, then you would get a 2-dimensional array and so on. Okay, so I applied softmax function on each element of that of that array. So let's see. Next is so again we assign. Okay, let's see. So A is a NumPy array with a collection of list elements, and so that's a. If you look at the A itself, it prints out just like a list. But if you look at its type, you can see that it's a NumPy ND array. And if you look at its shape, so you can access its shape. So every time you are confused, oh, what's the shape of this particular array? Is it 2 dimensions? It's and how many number of if it's 2 dimensions, how many number of rows and columns? Then you can call dot shape, and you can also see the data type of this particular array. Because numbers were all integers, it's int 64. And if you have different, if you have a float in there, then the whole array is of the type float. Okay. We'll have the data type float. So that's about NumPy arrays, and NumPy arrays have a lot of interesting functionality that you will start working through, and you will see that in the first assignment you need to understand the logic regression code that I gave, so, which has a lot of NumPy arrays and vector indexing and so on. So let's see. So here, for example, this matrix B, because it has 2 rows and 3 columns, you can index from the first row onwards and up to the second row. I mean, second row doesn't exist, so up to 0 and 1, basically. The first 2, sorry, up to the second, I apologize. The second column exists. So you can see that 1, 2, and 3. So 0th column is 1, 1. First column is 2, 2, and the third column is 3, 3. So you can index. So basically, what we're trying to do is get 1, 2 here. So this would be the first row onwards and up to, and not including the second column. Okay, column indexing again is from 0. So if you do that, then you get C, which is basically 1, 2. So the bottom left part of this matrix. Okay. And similarly, you can just get if you index exactly so there's a little bit of difference here. If you index exactly the first row here and pick the first two elements in column wise, then if you look at its shape, the shape is actually 2, nothing, whereas the first guy shape is 1, 2. So just be careful about these aspects. The difference between this and this is just a colon in the first indexing of this ND array. You can also do comparisons, and comparisons can lead to selection of rows and columns. So, for example, b greater than 2 is going to compare every element with b. So b is 1, 2, 3, 1, 2, 3. So every element with strictly greater than 2 is going to be first 4 entries are going to be false, and then only the last column is true. And then if you print a b such that b greater than 2, so then this is going to be the index, okay, which you're inserting into b bracket. So b greater than 2 will produce this array, and then you're indexing b with that. So you just want the last column. Okay, so that's 3, 3. So that's NumPy indexing. A very quick introduction to NumPy indexing, and the usual, once you have arrays, you can multiply, and so note that x times y is going to be element-wise multiplication, whereas x dot is going to be vector product. And there's also at-the-rate operation for, I think, matrix vector and matrix multiplication. So you should read the NumPy documentation to figure that out. There are some nice functions also you can get. For example, if x is a NumPy array with 1, 2, 3, and 4. If I do x dot sum, it's going to add up all the elements. So 1 plus 2 plus 3 plus 4. So that's 10. And similarly, x transpose will give you the transpose of 1, 2, 3, 4. This will be 1 and 3 and 2 and 4. Okay. And finally, just one use of image manipulation. There are actually many modules with which you can manipulate images. Here we're just showing with SciPy an image IO. So, and also I'm using Matplotlib. So it's just a way to show an image. So plot.imshow can show an image. So that's a very quick intro to Python. Let me get back to the slide deck. Okay, as I said earlier, you can use python.org, and you can download Python installers from python.org, or you can use Anaconda Python. So either one works. So here I said I use IPython. IPython is just the same as Jupyter. So you can install Jupyter once you install Python and pip, or Conda. Okay. So okay. Yeah, and here I'm just showing how to start Jupyter or IPython. So, I mean, first install it. You can do pip install, or you can do Conda install. And there's also this notion of environments. I'm not going to talk about that, but you will see that it's a good practice to create a virtual environment for your, whatever activities you do, because then it doesn't affect the system-wide Python, for example. Especially if you don't use Conda, you can use virtual env. Okay. Okay, so this is starting the notebook. I'm going to skip most of it because we just discussed yeah, we just discussed many of the cells, and of course, 15 minutes is not enough to discuss many of the features of Python. And this, what I discuss is very basic things. You will basically learn a little bit more about Python as you do the exercises in this course. So I think one homework activity you could have tried was to load up the logistic regression classifier, a linear classifier example dot note, linear classifier example that notebook, and try it yourself whether to see how the classification works, which I showed towards the end of um, last lecture. Okay, so that's the walkthrough of Python. Any questions at this point before I actually pick up the two important topics today? So if you have not worked with Python at all and are facing getting started with Python issues, essentially installation or using your favorite text editor or using the Spider IDE that comes with it, or and so on, just let us know on Slack, or you can definitely send me an email, and we can work through it. Okay. For the rest of this lecture, we really don't need Python code yet. I mean, there may be some snippets where I want to show the code. Okay, so let's start with feedforward neural networks. So last time we looked at a specific type of model, which is this, okay, which is a linear model. And essentially, we're going to build on top of it by composing multiple functions. So what is first of all, what is a function? Function is a mapping, which produces, so F is a mapping which goes from some input, let's call it X, to some output Y, right? So last time we saw this particular function where W was a matrix, B was a vector, and X was a vector. Now, a feedforward neural network is essentially built on this idea and with some additional twists. So most important component will be a nonlinearity. So here's an example of so we'll start with an example. So here's an example of a two-layer model, okay? So when I say a model, it's just a function. And so the two-layer model will have a bunch of parameters, W1, B1, and W2 and B2, okay? So if you compare with linear model had I was noting two parameters W and B, and the model itself, was this. Now this two-layer model with these four parameter sets or four parameter elements, W1, B1, W2, B2, is gonna look like this. So this is an example. So W2 times a max operation on a input plus a vector. Okay, so W2 is a matrix, B2 is going to be a vector, and now W1 x1 plus B1, we already know from last time it's a vector. Now max of 0 comma a vector is going to be an element-wise operation. So a max of a 0 and a vector such as 1 and minus 1 would be 1 and 0. Okay, so this is a max operation. So it's just a max operation we know for two scalars or two numbers. Give me the output which is the highest number. Here it's just element wise. Okay. Now, if so, let's do some rudimentary calculations. So let's say x is d-dimensional. Sorry. Then since x is d-dimensional, the matrix that multiplies with it has to have one of its dimensions d. Right. So I think. Yeah, so this should be, yeah, Q cross D, okay. Yeah, sorry, there's a typo there. So W1 should be Q cross D. So it's just matching the dimensions. And B1 has to be Q dimensional. Similarly, W2 is going to be, let me just change this, P cross Q. So W2 is going to be P cross Q because W1x plus B1 is going to be Q dimensional. So this is going to be Q dimensional. which means like, let's say Q is 5, so it's 5-dimensional vector. So max of 0, 5-dimensional vector, you'll get some, some vector like this, which is still going to be 5-dimensional. And then W2 has to multiply with a 5-dimensional vector and produce an output. Okay, so let's assume that the output dimension is P, because let's say we have P classes to predict, scores for, as in how likely is it that my input is of class, 1, 2, 3, or P. So I need to produce P scores. Let's say one of the scores is highest is what I consider to be, with which I'm going to predict that it's of that class. So W2 is going to be P cross Q, and then B2 itself is also going to be P dimensional. Okay, this is just a very quick check for dimensions. You'll see that when you code up neural networks in many of the packages, there will be some friction in identifying dimensions. Okay, as you just saw, so the dimensions of W1x1, W1x plus B1 and W2 should match. Okay, so for example, W1x plus B1 has to be Q dimensional, and W2 one of the dimensions has to be Q. Okay, has to have Q elements. Okay, so this is a two-layer model, and I'm going to explain why this is a two-layer model. But first, let me focus on this operation, this max operation. Okay, this max operation is an example of a nonlinearity, because I'll show you in a couple of slides. But there are many such operations that you can have. So max was an element. So max was a function which was taking an input. In this case, the input was W1x plus B1. So that's the input. Max of let's assume that one of the components is a fixed thing, so it's not really an input. Then max is taking an input and producing an output. Now that input-output relationship could be linear or nonlinear. Okay, so it turns out, we'll see that for max it's nonlinear, so that's why it's a nonlinearity. But there are many nonlinearities. Okay, so for example, if you have a function which is whatever input you give, I just spit out the same number. There is no nonlinearity. It's a linear function. But this is a function that we just discussed. It takes an input x, but if x is less than 0, then it produces 0. If x is greater than 0, it produces that number itself. So that's called a Relu Non-Linearity, RELU. It stands for Rectified Linear Unit. But there are many non-linearities, and this slide is just showing that there are many variations that people have proposed. But we'll just look at a couple of popular ones. So one of them is Relu. The other ones are like tanh and Sigmoid. Okay. And in this two-layer model, I specifically picked max of 0, whatever the other input is. But why that, right? You can use, as I showed you, this is a menu of nonlinearities. So why can't we pick one of these? We can pick them, and certainly then the model will be a different model. Okay, within the class of feedforward neural networks, it will be a different model specification. So let's actually spend some time on these nonlinearities just to get a sense of the nonlinearity aspect, right? So let's start with a sigmoid. A sigmoid, just to recall, is equal to 1 by 1 plus e to the power minus x. Okay. I've been repeating sigmoid quite a bit because even in last lecture, we were doing backprop with one of the nodes being a sigmoid. So sigmoid, it actually, since let's say x is a scalar, so scalar just means a single number, and this notation just means it belongs to a real number, so it can take any value, negative, minus 100, all the way to 10,000, whatever it is. Okay, so if you make x vary from some large negative number to some positive number, in this plot, I'm just varying from -6 to 6. And if you compute this number 1 by 1 plus e to the power minus x and plot it, then you'll see that this is the curve you get. Okay, it's 1 by 1 plus e to the power minus x. Okay, so straight away you can see that as x varies, the value of y is not. So this is, let's say, the y-axis or the function output. It's not varying linearly. For example, if I vary x from 2 to 6, which is 2 units here, y only varied from some value to some value. Okay, maybe 0.8 to 1. Okay, whereas if I varied x by from 0 to 2, then the variation was from 0.5 to 0.8. Okay, so there's a difference in this variation, and that's why it's a nonlinear function. But you can see a couple of other things. One is that there is a some sort of a saturation going on, which is that this nonlinearity, the maximum value you can take, let's say x is infinity, okay, then e to the power minus x is going to be what, 0, because minus x is going to be minus infinity, e to the power minus infinity. We know what the e to the power something function is. It's always positive, and it's like an exponential function, right? E to the power x. Okay, so even if x goes to minus infinity, e to the power minus x never goes below 0. In fact, it will go to 0. Okay, so so the largest value it can take is actually 1, the sigmoid function, and the smallest value it can take is, because e to the power minus x cannot go below 0, but it can go all the way to infinity, e to the power x or e to the power minus x. This number, it's the denominator can blow up. For example, if x is minus infinity or minus 10,000, let's say, then if x is minus 10,000, then minus of that is 10,000. So e to the power 10,000, we know how big that number is going to be, huge number. 1 by e to the power 10,000, because plus 1 doesn't really matter, is going to be some number which is very small. Okay, so the smallest value that the sigmoid can take is 0. Okay, and at x is 0, you can see that e to the power minus x or minus e to the power 0 is basically 1. So 1 by 1 plus 1 is 1/2. Okay, so at 0 it's 1/2. So anyway, this is a nonlinearity. So this I can apply to any incoming scalar value or element wise on a vector as well. Okay, and so it basically, if the number is is varying all over the place, it's negative, positive, this nonlinearity is going to squish that number to a number which is between 0 and 1. Okay. So the effect that I talked about, where for large positive values, it kind of doesn't change. It's around, quite a bit around 1, right? Pretty much around 1 after 6, or even before 6. And it's pretty much around 0 below minus 6. So any x value below minus 6 is kind of pretty much 0. So that is essentially a, you can call it a saturation. So this type of nonlinearity, if you use in a neural network, and we're going to look at, so in the sense, for example, if I specify this function with a sigmoid nonlinearity, right, instead of max here, if I use sigmoid, you can imagine that if my operating regime, let's say, for example, when I, so when I have, for example, I have a bunch of the W1 B1 and W2 B2 it's fixed at some particular candidate model values, okay, because those are the parameters of the model. And if it turns out that the values of these guys are such that we are operating in this region, okay, this circular region or this region, then essentially what happens. So let's say if there is we're doing this sigmoid operation, and there's an incoming gradient, okay, gradient of some further down output, like h with respect to this node's output g. Okay, so that's a gradient that's passed back to us in the backdrop of operation, and the gradient of that's multiplied with the local gradient. So that's the gradient of g with respect to gradient of z. Okay, so that's this guy. Multiply with the incoming gradient and pass it backward, right? But if you look at the gradient of g with respect to z, if z is around 6, then no matter how much I change z, g is not changing that much. So this gradient is actually close to 0. Okay, so this number is essentially close to 0. Similarly, if z is highly negative, then the rate of change of g with respect to z is also close to 0. Okay, so this is essentially what it's doing is whatever gradient I get, I'm multiplying with a number which is essentially 0 and then passing it backward. So that way, it's actually not. That means that whatever information, because this gradient is some sort of information of which direction to go to get to a better model, right? Some W1, B1, W2, B2 to some new W1, B1, W2, B2. Remember, we were talking about gradient descent last time. So this is not good because it kills the gradient, and we stay at the same place, for example. Okay, and so that's saturation. And there's another aspect, which is that this nonlinearity is centered around 0.5, in the sense that whatever numbers are on the input side, let's say they are evenly distributed between -6 and 6, on the output side, all the numbers are between 0 and 1. So it's not symmetric around 0, which could be an issue as well. I mean, if you prefer a function which is symmetric around 0, maybe you can downshift it with -1/2, for example. So you can do let's call this function sigma, because it's a sigmoid function. Whatever is the input here, z -1/2. So this would be centered around 0, for example, right? So that's the sigmoid function. Let's talk about another nonlinearity, just to get a sense of how this other nonlinearity looks like. So there's this nonlinearity called tanh, which is quite popular in early generation neural networks. So tanh is it's a function whose curve, and you can look up on Wikipedia, whose curve looks like this. Sorry, that was. Yeah, so this is the tanh function, and you can see that this almost looks like a sigmoid, but with the saturation aspects here, but it is centered around 0, and it goes from 1 to -1, right? But if I do sigma z, so the sigmoid function, and subtract half so that it centers around 0 on the y-axis, then it will be going from 1/2 to -1/2, okay, uh, on the output direction, because I just subtracted 1/2. If it was not the case, it was going from 0 to 1, right, on the output side. So those are two nonlinearities. You can still use them, and I think we can use them on basic um, uh, uh, recurrent neural networks that we'll see later. But yeah, in fact, in RNNs, there will be a place where we'll use sigmoid nonlinearity and so on. So there's a question about, will there be a problem if it's not centered at 0? No, it's not a problem as such. It's a property of this function. So essentially, you cannot expect. So once I put this nonlinearity, all the numbers which, let's say my input has negative numbers and positive numbers. Let's say it's a huge vector with negative and positive numbers. At the end of, if there's a computation graph where there's a bunch of sigmoids, nonlinearities, the output side, all the numbers are shifted to 0. It's shifted above 0. Okay, that's all. I mean, it's just a property. It's a property that's also true for example, Relu. So it's something that you may be interested in, because maybe you want transformations which keep negative, keep an equal number of negative numbers. Okay, so that's something that comes from, maybe you prefer negative numbers to be there at the function output. For example, let's say you have a model, right? So let's say this model. We're going to describe a little bit more about this model. In this model, as there will be no negative number on the output vector, the p dimensional vector, as long as all the entries of W2 are positive and all the entries of V2 are positive, because this guy will always produce positive numbers. Okay. If W2 and V2 also have positive numbers, I'll only get positive numbers. Maybe I'm trying to predict maybe it's a regression problem, and we'll see that we can also use neural networks for regression. If it's a regression problem, it turns out that I'm trying to predict a negative number. Okay, some sales, and sales can, rate of change of sales, and that can be negative. Okay, so if it turns out that these parameters are positive, then you'll never get a negative number. Okay, so that's something that you can think about if it's a concern. You'll see that sometimes optimization techniques may need, and one of the optimization technique that we briefly mentioned last time was gradient descent, may get influenced by the zero-centeredness or not. One, unrelated thing that you might have seen, for example, with PCA, is that you would want your data to be zero-centered for the principal components to make sense, right? So unrelated, but here it's just, it has no impact. It's a property, but it's worth pointing out, because there is a different nonlinearity which kind of fixes that, right? A tanh is almost, kind of a similar S-shaped curve, where it's going from -1 to 1. So it's kind of symmetric. Okay. Okay, so let's talk about the nonlinearity that we introduced in the network. So, in the model. So remember, our model was f of x with a bunch of parameters: w1, v1, w2, w2, and v2. And there we said there was a max operation. So W2 times max of some input plus B2. So it's not input. In between, there was a W1 times X plus B1. Okay, so that I'm not writing it explicitly here. And there's a max of 0 comma that. Sorry. So that nonlinearity is called a rectified linear unit nonlinearity. That's what I think the original paper uh, mentioned it as. I mean, it has this nonlinearity has been probably been there before as well, um, uh, and that's where it gets that name rectification. It's from, I guess, electrical engineering. So it's basically looks like this. So this dark blue plot is this nonlinearity. As I said, if you're greater than x, you just output x, and if you're less than if the input is less than, for example, 0, you just output 0. So x-axis is the input, y-axis is the output. So there is a clipping of all the negative numbers back to 0, right? So that's a rectified linear unit, and essentially what you can think of it is that on the positive side, if my input is positive, then if you think of backprop step, let's say there's somewhere I use this nonlinearity in the backprop step, and you can think of that as a node, right? A computational node. In the backprop step, I get this input gradient because as long as this particular value is positive, z. Remember, in the forward computation, z takes some value. So let's say z is 2, okay, some value. And if I want to now backprop, because z is positive, I just pretty much return back the gradient that I got, because gradient of g with respect to z is 1. Okay, here the gradient is 1, here the gradient is 0. And if z is minus 2 in the forward computation, z is minus 2, then clearly you output 0 anyway in the forward computation. But also when you get back a gradient number, you'll be multiplying it with 0, so there is no gradient which is passed back. Okay? So when you pass back, when z is positive, there is no vanishing gradient. Vanishing just means there is a number that is being passed back through this node, so it's like a transparent node, as if it doesn't exist. But if it is negative, then there is a vanishing gradient problem. Not a problem, but the input information is completely gone because you multiply with this locally with a 0. Okay, and this particular nonlinearity, people have kind of pretty much decided that let's use this because empirically it was observed to fit really well to data. And you'll see that we'll use this nonlinearity in many neural networks, for example, convolutional neural networks. And this particular nonlinearity seems to give very good empirical results. And there's a bunch of theory on why it makes sense under a lot of assumptions, but for us, we'll focus on empirically validated, I guess, techniques and design choices. So this point here, which is this one, is that if you somehow happen to start your W1, B1, W2, B2 numbers such that no matter what excess you input, the intermediate z's are always negative, then you essentially have a dead ReLU. In the sense, there is no forward path. Because those computation nodes will always be producing 0, and they'll not be passing gradients back. So they're essentially dead. Okay, in some sense. So the initialization matters, and we'll talk about initialization of these parameters later on. Okay. So let's come back to the feedforward neural network. I just wrote the functional form. Let me repeat it here. It's W2 times max of 0, comma W1 times X plus B1 plus B2. Okay, and we just did the dimensionality computation earlier. Now let's give some names here. So this is actually called a 2-layer neural network. Okay, a 2-layer feedforward neural network. And it has, so there's because I'm saying it's 2 layers, so there has to be 2 layers. So there is a input layer, a hidden layer, and an output layer. So you just always say 2-layer just means, so if you include input and output, just subtract -1, okay? So because there are 3 parts, if you ignore the output, then there are 2 layers, okay? Input layer and hidden layer. And this is a representation, a picture diagram of this 2-layer network, which helps us understand what's going on. So this picture has a bunch of nodes. Okay, these are not necessarily the computational graph nodes that I was talking about last time, but you'll see that they are pretty much the same. And there's going to be and we saw the nonlinearity examples from before, and there's also this notion of an activation. Okay, so those are the words that I want to use, and one of the layers is going to be a hidden layer. So we're going to talk about that right now. So in this two-layer model that we are as a running example, the number of layers is basically, so if you want to, so why I'm saying it's two layers is because I'm parameterizing that using one set of parameters and another set of parameters. So you can think of that as representing the number of layers. So and the same picture from previous figure, I've drawn it vertically. So there's an input layer, hidden layer, and output layer. And at this point itself, you can say, oh, why am I, I'm talking about two-layer example, but why should the number of layers be just two? It could be many more than that. I can have many more these green things copied. And also, what are these nodes? And we're going to discuss about what are these nodes and why have I drawn 4 here and why I've drawn 3 here and why I've drawn 4 here, for example. We're going to discuss that right now. So yeah, so this node, so let's go back to one of the figures. So there was 3 nodes here, and let's focus on one side. I mean, there was also an output layer. I don't remember how many nodes were that, 2, let's say. So anyway, so and I call this input layer. So the 3 nodes or 3 circles here in this graph, a representation graph for that neural network, just represent, let's essentially kind of tell us that the input dimension x is 3. Okay. Now these edges here say that so think of this as x1, x2, and x3, 3 coordinates, x1, x2, and x3 of the input layer. And these 3 are going to this node here, and it has an output. Maybe it's out. Okay. Now, so this node here is essentially, since there are 4 nodes here, let's assume that q is equal to 4. Okay, and let's assume that let me quickly see the uh, oops. Sorry. Okay, there were 2. So let me go back. Okay, and p is equal to 2. Okay. Now this W1 matrix in our function, uh, W1 matrix is going to be uh, let's just do the W1 matrix. It's going to be 4 cross 3 because Q was 4 and the input was 3 dimensions. So there's going to be a bunch of rows. There's going to be 4 rows. Okay, and each row will have 3 elements. So maybe let's call this A, B, and C for simplicity. And the remaining other rows will have additional elements. So um, this first node here is essentially, think of it as a computational node, which is computing this this function, which is a times x1 plus b times x2 plus c times x3, and then applying the nonlinearity, which is max of, I mean, for example, max of 0 comma its input. Okay, let's say this is c. Okay, so this so that's why, so these edges represent that these 3 are inputs to this node. Okay, so x1 and x2 and x3 are inputs. The node has local, I guess, parameters, or essentially or the edges themselves have parameters a, b, and c. Okay, and the computation that's happening is element-wise multiplication between the edge weights, essentially, which are essentially the rows of this W1 matrix, times the x1, x2, x3 element-wise, and then sum them up. and that's the input to this node, and I pass it through a nonlinearity, and the output is the output here, okay? And it's whatever is output, let's call it Z prime, is sent back to sent forward to these guys, these two nodes, and these edges also represent that there may be additional weights D and E here. Okay, so that's the representation of that's the that's the interpretation of this picture. So let's come back to uh, so now we have a network. This example, it was a two-layer network. And we just described why this has 4 nodes here. Let's say when Q is 4. And you can see that this computation here, W2, this, this computation here is split into a layer-wise computation, which is this one in the box, max of 0, W1x plus D1. That's going to be the computation whose output, up to this point. And then that four-dimensional vector, which is the hidden layer output, is going to be multiplied with W2, and then a vector B2 will be added, which is going to be 2-dimensional. And W2 is going to be 2 cross 4 dimensions. Okay. So that's the relation between this figure, which is a layer-wise representation. So there's one layer, and this, a computation happening up to hidden layer and its output, and then a computation happening from hidden layer to the outputs. Okay. And here for this layer is W2 and B2, which are in use, and this input to hidden layer W1 and B1 are in use. Will it be a vector of 2 dimension in the output layer? Yes, that's great. Yeah. Yes, the question was, will it be a 2-dimensional output vector? Yes. So here P is 2 in this picture. So we'll have a 2-dimensional output. So how will we know when to use sigmoid and when to use saturated? So saturation happens depends on the numbers, okay? But when to use sigmoid, you can always use sigmoid and see what's, so when you change, when you go back, let me go back here. When you change the choice of the nonlinearity, so in the function example that I was going through, in these few slides here, I was just using max of x comma 0, but that's just one nonlinearity. There are so many other nonlinearities here. You can always change that, but that just changes a function, right? Just like in a model, if I change the parameter from one number to another, it's a different model. Similarly, I'm just changing the structure of the model itself. So the moment I change from max of 0, x comma 0 to the sigmoid nonlinearity, it's a different function, clearly, right? And it's a different function, and it may have a different it may capture different patterns in the data. Maybe for some data, sigmoid is good. For some data, Relu is good, and so on. So a priori, we cannot really say, because these are 2 different functions. We can't really say which one is more useful. But empirically, it's been seen that at least these days, Relu is a good contender, a good first choice for a nonlinearity. And folks in research probably don't experiment too much with the choice of nonlinearity. They have already done it, and you can see so many examples here, as well as there are some examples in recent years. But folks focus on some other aspects of the neural networks. But you can certainly use any and try and see if one works better than the other in terms of reducing your training loss and so on, or cross-validation loss and so on. If it is going to result in the same place we are already at, where would saturated be helpful if it is going to result in the same place we are already at? So saturation is what could be useful or may not be useful. So in this, in this slide, I was just mentioning a couple of properties that are seen by the sigmoid nonlinearity. That very high values and very low values, the gradient doesn't get passed back. Okay, in backprop, that could be an issue. Okay. For example, the same thing on the Relu nonlinearity. If the input is really large, the gradient is still passed back on the positive side. Except on the negative side, whatever be the value of the current value of z, for example here, If it's negative, no gradient is passed back. So these are different properties exhibited by different functions. And you compose, so if you can just look at this as a composition of functions, right? So initially I produced a vector, just matrix algebra here, multiply a vector with a matrix plus add a vector. So you just got a vector. And then I'm composing it with another function, max function. So that's just offsetting all the negative values to 0. I mean, not offsetting, sorry. Setting all the negative values to 0. And then I'm again composing that output. I'm composing with another linear function, which takes that output, multiplies it with W2, and adds B2. So it's just think of it as a composition of a bunch of functions. And that's why the layer view is useful. So some computation is happening here. An intermediate vector is created. And then a max operation happens, for example. And then again a linear transformation happens, and that you get an output, which is a bunch of scores. Okay, so let's now talk about its relation to backpropagation, because that's a key concept that we learned last time. So if you create a mini batch of size b, and think of the size b as 64, 32, generally multiples of 2. You can also choose 10 to whatever. Some size, okay? So if you have 1,000 examples, you don't want to compute gradient with respect to all the 1,000 examples. So remember this L data. And an approximation of that is just picking a few examples, acting as if for this forward pass and backward pass for computation of gradients to update my parameters, as if I only have a limited data, which is only 64 of the full data and so on, right? So if you choose a mini batch size, I'll get to that question pretty soon. If you choose a mini batch size, then the forward pass would be just the last computations over each of the examples in the batch. And if there's a regularization, okay, you can regularize both, for example, these two matrices, these vectors, and so on. And typically people regularize mostly these weight matrices. Then you can get the overall loss for this batch. Remember, L is equal to some lambda times regularizer plus whatever the value that I got, plus sum over the items in the batch of items in the batch of the loss values there. Okay. So once you get this loss, you want to backprop. So you want to find gradient with respect to W1, gradient of L with respect to P1, and so on. So by the way, these are not, so W1 and for example, W1 is a matrix. So gradient with respect to matrix is going to be a bunch of numbers which is the same size as the matrix itself. So these are not easy to hand compute, but once you get these, then you can update the current parameters by moving in the direction of negative gradient. And that's why we saw, for example, we would update W1 new with W1 old minus some number, let's say 0.1. It's typically called the learning rate times the gradient of WL with respect to W1. This is what we would do. So now there's a question about, can we discuss different drawbacks of sigmoid activation or damage? Drawbacks, these are not really drawbacks. I mean, these are properties. Whether you think of it as a bad property or a good property depends on whether using that nonlinearity in your prediction model is good enough or not. Okay, so because at the end of the day, you care about prediction accuracy, out of sample, basically on test data. So whether using these different types of nonlinearities may have different influences on how you choose your optimization scheme. Okay, and also where you start with in terms of the initial parameters. For example, as I said, if let's say your data is all data, which means that the feature vectors are all negative, okay, and you just initialize W1, B1, W2, B2 to be negative, then you can see the problem, right? Because any future computation, any intermediate computation will always have negative numbers, and you don't really make any meaningful progress when you do this update, right? But if you chose your initialization of the initial parameter choices, W1, B1, W2, B2 to be random, and some of them are positive and some of them are negative, even if your data has all negative numbers, which is feature vectors in examples, maybe you can push them, maybe because of the random choice of W1 matrix and so on at the beginning. Maybe some of the ReLUs are not dead in the sense that the Z that is at the input of input to these nodes is positive, and so you will still get a gradient flowing, and you'll probably move around the parameter space fine. Okay. So there's a question, will there be a case in which a local gradient of these functions are small and disallow the forward propagation? Yeah, so gradients can be small, right? So Relu, it was a case that here the gradient was exactly 0, but for sigmoid, actually, the gradient is not exactly 0. It's very close to 0, like 10 to the power minus 3, or maybe 10 to the power minus 2, or 10 to the power minus 5, and so on. So there's going to be some small number. Okay, there will be some signal, but it'll get attenuated quite a bit if you're far away from, if your numbers are such that they're swinging too much. Okay, you can actually measure these things. So let's say you had a feedforward neural network and you're doing gradient descent. You can actually look at, sorry, let me go back here. So let's say you're doing these steps, right? So you hand-coded gradient descent, although you would not do this, but let's say you hand-coded gradient descent. You can actually look at statistics of these gradients. So this is actually gradient of loss all the way to the parameters, but you can also keep track of the intermediate gradients, right? So, I mean, if you have a simple enough computation graph, and if you're actually doing backprop, you can actually remember them and log them and plot them. For example, even though if here it's a matrix. If it's a matrix, you can look at its matrix norm to see if if it's all zeros or if it's like exploding, in the sense it's all huge numbers. You can actually look at some empirical histograms of these gradients while training and get a sense of whether any of these properties of nonlinearities are affecting you or not. So let's look at feedforward neural net now. Um, so it's been an hour. So actually, so what I'll do, so let's take a break for a 10 minutes. Let's resume at 4:45. Right after resuming, I'm gonna again look at a Jupyter notebook where I will look at the feedforward code instead of looking at the slides. Okay. Okay. So let's take a break for 10 minutes. Resume at 4:45. Okay. So let's resume. Okay. So I'm just loading a different uh, notebook from that directory. So you should be able to load uh, notebooks from that directory by doing the git clone and so on. You should get comfortable with that. If you're facing trouble, ask on Slack or email me directly. I also wanted to show you another thing, which is yeah, which is how to set up Jupyter. So this page is actually from another course that I'm currently offering. So you can look at actually uh, the basics of setting up is setting up your Jupyter notebook. For example, certainly you can start Jupyter notebook on your own machine for a preliminary task, and you will probably also use Google Colab, which is essentially like a Jupyter notebook. Uh, but you should also probably see, for example, this particular step on this web page, and I can share this link on the chat. So you can see how to install, for example, the Miniconda distribution, how to create an environment. So this is just best practices. Actually, you don't have to create an environment to get started with Jupyter Notebook, but so it's a cleaner way to do that in this way. So you should probably read, have a look at this particular document, this particular page, and you can also see how to install PyTorch. In particular, Jupyter Notebook, it's always good to have a password and other configurations if you want. And if you're running Jupyter Notebook on a server, which is how I'm doing it here, where I'm going to talk about the feedforward neural network classifier now. I actually ran So I started the Jupyter notebook under a screen session. Okay, screen session just ensures that even if you are disconnected from the server, so this notebook that I'm running, where I'm opening this in my browser, is actually not locally run Jupyter notebook. Okay, it's running from a server. So so starting a screen session and running a Jupyter notebook, and then how to tunnel to connect to that particular Jupyter notebook is also given here. So I would suggest looking at uh, 3 and 4 to get a sense of how to get Jupyter notebook set up. Now let me go back to Feedforward network classifier. So in this notebook, we saw last time what the data was. So the data is essentially like synthetically created data. It has 3 classes, and there are 100 examples per class. There's the yellow, red, and blue or purple class. And the feedforward network we just discussed in the previous slides is what's written here. So we just chose an arbitrary number of hidden layer, the queue, the number of I guess rows of W1. Um, so actually, I should not refer to rows and columns at W1 because you'll see that there are things which are transposed in this code for efficiency reasons. But this is the number of hidden units. Okay, so the number of in that picture in the diagram that we saw earlier, where I had 3 nodes at the input layer, 4 nodes in the hidden layer. The 4 nodes, the number of nodes essentially, each node essentially represents a neuron in some sense, and we're going to discuss that more today. And so how many number of units do you want in the hidden layer? Okay, how many number of neurons you want in the hidden layer? And we saw what the neuron computation was we just saw that it's just a sum of all the inputs, element-wise multiplication with some numbers, essentially the row of the matrix W, and then do the nonlinearity. Yeah. It's just checking if I was recording. But so then there's the initialization. So so you can see that W1, B1 instead of W1, B1, I just saw W and B. And there's also W2 and B2. Okay, so K is the number of classes. Here, the number of classes is 3. Let me actually, I think I ran this. Okay, run the model. Okay, and then if I look at so W is going to be huge matrix. So if we look at this number, then it's basically 2 rows from here to here and from here to here. Okay. Why does it have, sorry, it has 2 columns, sorry. So wait a second. Yeah, sorry, 2 rows. So D is the dimension of the input. So input is 2 dimensions if you look at the input x dot shape, which is the x dot shape, and then shape will produce 2 numbers, the number of rows and the number of columns. The number of columns is in the index 1, and so that's why I'm storing it as D. And number of classes, I'm just I can write it as 3 directly because I can eyeball it here. Or you can see, because Y, which is the class labels, were 0, 1, and 2, it started from 0 indexing, so max of Y is going to be 2 because so Y is going to be a vector where every row, every element, every coordinate is going to be the class corresponding to that example. Like the third coordinate will be the class corresponding to the third example, and 10th coordinate would be class corresponding to the 10th example, and so on. Okay. But all these class values, they're going to be 0 or 1 or 2. That's how I'm representing the 3 classes: 0, class 1, class 2. And so max of Y will be one of these 3 numbers, maximum of these 3 numbers, which is going to be 2. And since the number of classes is 3, I just added a +1 here. And so this is the initialization. So you can see that I'm initializing such that they're negative numbers as well as positive numbers. And this code is actually tied to the specific nonlinearity that we're using. And in particular, in the slides, we're using the Relu nonlinearity. So in fact, the code is pretty dependent on the Relu nonlinearity. And in your assignment, there is an exercise where you change the nonlinearity and try to compute the backdrop steps. So let's just look at the forward operation currently. So let's see. So we plotted the data. So far nothing much. So now we are setting up the model. So the model has these 4 parameters, W1, B1, or WB, and W2, B2, and they have been initialized to some random numbers. I'm also picking the regularization. Remember the lambda in front of the regularization term, so that I'm picking as 10 to the power minus 3. We don't need W. Okay, so now, so what is the number of examples? As I said, x dot shape bracket 1 was giving the number of dimensions of x, which is two-dimensional data, two-dimensional feature vector, right? And then unshaped bracket 0 will give you the number of examples. And we're going to take a step size to be equal to 1, actually. So it's the last step size. We can change it, and depending on that, you'll get different results. It's a choice in your algorithm. So that's an algorithm parameter, and the gradient descent parameter. Now, the gradient descent loop, we're going to run here. It's hard coded to 10,000 steps. So I'm going to do, first candidate set of W1, B1, W2, B2, all the way to the 10,000 candidate set of W1, B1, W2, B2. Okay, so there's, I'm not going to break in between. And so let's look at what the, and so here is the forward pass up to this point. So first you compute. So what we're doing is in the gradient descent is we're not doing any batching. So this particular code is saying, oh, well, actually you'll see that the number of examples is just 300. Okay. Yes, so somebody asked where's the data file. So actually data file is, if you don't have the data file, just open the other notebook. So in this notebook's things, you will see a data linear classifier. It just shows you how the data was generated. It's not really critical, but it actually is a deterministic data generation process with some noise added here. So if you run this, it's just one cell, the data gets dumped into the current directory. Okay, so you can change this data. You can actually create 3 classes, 4 classes, and so on. So you can change the classes. So then the model is kind of hard coded, and the number of steps and in gradient descent and all that is in the other file, which is somewhat hard coded. The model is hard coded in the sense that I'm reliant on the max of 0, x nonlinearity in that two layer network for the whole computation to be correct in terms of gradient descent, changing from parameters to parameters. But you can certainly go from 2 classes to 3 classes to 4 classes, as well as the input dimension you can change from two dimensions to 3 dimensions, 4 dimensions. Okay. So actually the classifier is pretty much the same as the linear classifier. So the only difference is that in the linear classifier, the linear classifier, the model was just W1B, and gradient descent was, I was only doing 200 steps, but you can change it to 10,000 if you want. And there was a forward step. Okay? The forward pass was just, whatever is the x, multiply with the matrix to get some intermediate intermediate values, in the sense that intermediate values plus, because I need to add the b vector. And if I add that, I'll get the scores. Okay, and so if you just look at this row, it's actually a vectorized operation. X is actually 200 cross, sorry, X is 300 cross a 2-dimensional matrix, and W is actually equal to 2 cross 3-dimensional matrix. Okay, so W is 2 cross 3-dimensional. I mean, you can just see that here. It's T is 2 and K is 3. So W is 2 cross 3, and X is 300 cross 2. Okay, so you can multiply that. You'll get 300 numbers plus. Sorry, you'll get 300 times 3. Yeah, so 300 cross 3 numbers plus B. Now B is going to be just a 1 cross 3-dimensional vector. Now this guy, as I said, is 300 cross 3. This is 1 cross 3. So the way the addition happens is this 1 cross 3 gets added to every row in your 300 cross 3 matrix. Okay, so that's called broadcasting. So this is still a valid operation. And what you get here is scores. And the scores matrix is actually a 300 cross 3, where 300 is the number of samples, by the way. It's 300 cross 3, where each row is essentially the scores for that example. So the first row has a bunch of scores, 3 numbers, and those 3 numbers represent, for that first example, which class you belong to. Okay, so the first score represents how much do you think you belong to class 1. Second coordinate of the first row represents whether it belongs to class 1 and class 2 and so on, 0, class 0, class 1, class 2. Okay, and then you do a softmax operation. Remember last time we were doing that to get these numbers between 0 and 1 and sum up to 1. And so that softmax operation happens by this vectorized steps, okay, where np.x is just the e to the power operation. Now, e to the power operation is just for a single number, but if you pass a matrix, then it does e to the power every cell of that matrix or every entry in that matrix. Okay, so you're doing e to the power of that divided by the sum of e to the power everything in that row. Okay, so everything in that row. So that's why these arguments are important. Keep dimensions being true and access being 1 and so on. So pay careful attention to this vectorized operation. Okay, so that's what's happening in linear classifier. In feedforward network, very similar forward step. First you create first you get the np.x, w and b. So that's the operation that you saw in the linear classifier case. But now you do an np.maximum. Okay, so the max function is present in the numpy package, which we have short form to np. But you can certainly write your own function. So you can write a def max function which takes 2 arguments, a and b, and then says which of the numbers is the highest. Okay, produces an output which is the one of the which of the numbers is the highest. Okay, you can certainly use your own function here. And scores are just so remember in the 2-layer network, first you compute a hidden layer. So that's going to be the dimension of the number of hidden layer dimension, which is q, and we chose q to be equal to 100 here. And so this is going to be a 100-dimensional vector per example. So you'll see that hidden layer is going to be because the number of examples is 300, so it's going to be 300 times 100. And then W2 is going to bring it back into again scores. And we remember scores were supposed to be, we only had 3 classes and we had 300 examples. So scores is going to be a matrix which is 300 rows and 3 columns. Okay. So, and again, you can do this step is the same as in the linear case. So I wanted to show you this. And then the next few lines are just computing the loss. Remember, there is no batching operation here. So we just have to compute the loss function, and we choose the loss function to be the softmax loss, or it's also called the cross entropy loss. You'll hear a lot in this course. And so we're just going to use that loss. And that loss is very simple. So once you get the probabilities, all you're saying is, oh, these are the probabilities that I'm predicting for each of the 3 classes. Let's pick example 1. So I'm predicting that the example 1 is class 0 with probability something, class 1 with probability something else, and probability with being in class 2 as something else, 3 numbers. Okay, but the true class, in the training data, it belongs to one of these classes. Okay, so the loss score is the negative of the log of the true class number. Okay, so if the first example happened to be in class 3, then you just look at what was the probability that you're computing for class 3, and that's just the negative log of that. Okay. So if you're predicting for the first example, class 3, the probability to be pretty high, maybe close to 1. Let's say it's actually exactly equal to 1. Then the negative log of 1 is actually 0. So the loss is 0 for if you predict exactly the right class. But let's say for this first example, the true class is 3 in your training data. I mean, you have that label, but your score, and so your score, and therefore your probability for that class 3 is close to 0. You're like completely mispredicting and predicting it to be class 1. So class, the third coordinate is very close to 0 probability. Then the negative log of number which is very close to 0 is going to be very large. Okay, log of 0 is essentially minus infinity, and negative of that is going to be infinity. So the loss is going to be really high because you misclassified. Okay, so that's how the loss works here, and I think I've explained it last time as well. And so you take the negative log of the probabilities of the appropriate coordinates. Okay, and that's why you'll see what this indexing, and that's what I was talking about indexing a little bit earlier in the Python walkthrough. So figure out what indexing is happening here, because y is actually saying 0, 1, 2, or one of these classes. Okay, and so you're actually flipping between different probabilities depending on depending on which row you are in. Okay, and you get completely the negative log, and you're summing them up. Okay, np.sum, and you're normalizing it. Normalization is not very critical because this is a constant. And then you're adding the regularization. So here we are regularizing both W and W2. Okay, so W1 and W2. So what is regularization we're doing here is we're multiplying W with itself. So remember, star is an element-wise operation. So every entry is getting multiplied by itself, whether it's negative or positive. Each entry now becomes positive. and then we're just summing up all the numbers. So it's some sort of L2 norm. Or remember, if you did in ridge regression, we were talking about L2 penalty. L2 regularize sum of squares penalty for the linear model. So it's very similar to that. Okay. Then we're adding those two as the final loss. And so up to this point is just a forward pass on the computation of loss. Now, from here onwards is a part of your assignment, so I'll not describe it. But from this line to this line is essentially you're computing the gradient of the loss with respect to all the parameters, W, W2, B1, and B2. Okay. Remember, at the end of this computation, you have to get a, for example, let's think of W. We saw W was a 100 cross two-dimensional matrix because 100 was a hidden dimension. Then the gradient of loss with respect to W also has to be the same dimension. Otherwise, these matrices, if you add it, of course, there could be errors with broadcasting, but you should not, make a mistake here. So once you do that, you're just doing the gradient descent step with step size. So you can change the step size and see what's going to happen. So in this case, in this example, with these settings, you see that the loss is some value. Lower the better, certainly. But you also want to get a sense of what is meant by what is 0.24 is. By just looking at the number, you wouldn't know whether it's a good number or not. So instead of just reporting losses, you can also report, for example, the confusion matrix. There are only 3 classes, so you can really look at the confusion and so on to get a sense. So here is the related to confusion matrix is the accuracy itself. That how many points in the test data, and I've done a hack here where test is the same as training. So I'm just asking for training accuracy. Although you should, in best practices, to compute accuracy either through cross validation or on a held out validation set. So here, accuracy is nothing but how many classes did I get correctly. Okay, this is the right class. If class of first example was 0, did I get the example, my prediction to be 0 or not? Okay, and it turns out accuracy is very high. And the reason for that, you can very easily eyeball through this plot, and this is a matplotlib plot. You can see that the class decision boundaries are this. Okay, so actually, it turns out that this feedforward neural network, 100 was maybe too much of a choice. You could change the number of hidden dimensions to maybe 10 or something and still see very similar pattern. And so you're able to capture all the reds in the red region, all the blues in the blue region, all the yellows in the yellow region. Okay, so that was the difference between going from the linear classifier to this nonlinear. First example of a nonlinear classifier. Nonlinear because of the max in the description of the function. Okay, so if there are any questions, it's a good time to ask while I switch between. Yeah. So I would suggest, I would encourage you guys to try this code out. Not so much, I mean, it seems quite verbose, but it will give you a sense of what's each line doing, and you can use print-based debugging, or there is actually a Python debugger, PDB. You can use PDB as well to kind of get a sense of what's happening in each step. You can actually break it into cells. You can drop the for loop, for example, in the code. You can draw the for loop to just 1 and get a sense of the dimensions of each object in there and see what's happening. Okay. So this is the same. And you actually also can see the same in at this URL. So playground.tensorflow.org. Actually, there's another URL called Teach with Google, I think. I don't remember, but I think it's on the class web page. So have a look at it. It's just in-browser visualizations for multi-class classifiers. So any questions about feedforward networks before we move on to the convolutional neural networks? Okay, so if there are no questions, let's move forward. So although I gave you an example of just a two-layer neural network, you can imagine I can just before I get into CNNs, I just want to tell you that you can actually use any type of So let me represent the network. It's just a function, right? So let me represent it as like this way. So I can have a network which is, I'm only representing this course. So it could be W10 times max of 0 comma W 9 um, times max of 0 comma W8. And you understand where I'm going here. So the and then many closures plus B10, for example. There's also going to be B9 and so on here. So there's essentially a composition of a bunch of functions, right? So starting with the linear function and nonlinear transformation. So a linear function, nonlinear transformation, another linear function, nonlinear transformation. So it's like, and that's why we draw it in a layer-wise fashion. So one layer to next layer to next layer, next layer, and so on. So, but the number of layers can be arbitrary. You can have a 10-layer feed-forward network, okay? Although you can imagine that if you have a 10-layer feed-forward network, you have to really have those dense matrices. Remember, there's a matrix involved with each layer. So if there are 10 layers, there are 10 matrices, and each matrix, of course, the dimensions will match with the preceding one and so on, but you'll have a lot of numbers. Okay. But I just wanted to show you that it's not just a 2-layer network, but you can have many layers. And this used to be, and feed-forward networks are quite useful when you're, for example, although next we're going to talk about CNNs, which are mostly about images, but for other data, for example, tabular data, if you want to use neural networks, feed-forward networks with some amount of depth, this is a depth, essentially, the number of compositions you're doing or the number of layers, with some depth, maybe actually a good class of models to fit your prediction model, whether it's a classifier or a regression model. Okay. Although we didn't talk about regression so far in the previous lecture and today so far, but regression, we just changed the score to a single dimensional score. So it will be essentially the same network, but the last matrix that you're multiplying, so for example here W10 is just going to be is going to produce a P, sorry, not P, but the number of rows of W10 would be just 1. Okay, so ultimately you're producing one score, and then your loss function would be some sort of squared loss where you're saying, oh, what is the true dependent variable value? Maybe it's 150 units, and what's your score? It's a one-dimensional score. Maybe it's 145. So then you do just a mean square estimate, it's mean square computation, which is just 145 minus 150 the whole square, for example, for that for that example I. Okay. So you can do regression pretty much in the same way. So let me now talk about convolutional neural networks. So these are actually very similar to feed-forward networks in the sense of there is actually a neuron or a node. Remember that graphical representation where there was a circle. As I was saying, that's essentially a neuron. So each neuron is associated with a bunch of weights. In the feed-forward network, I said, all the edges coming in, there were a bunch of weights, A1, A, B, and C. And we saw that for W1, this is essentially the first row of the W matrix. So this A, B, and C are the weights of the neuron. So A, B, and C, and then the input, if there is an input coming in, X1, X2, X3, then these would be called the weights of the neuron, although they're just the same as the rows of the W matrix, okay? And remember, just like there was a B1, so the first entry of the B1 vector would be also part of this neuron, okay, in terms of computation. And you can easily infer that yourself, whether you think in terms of matrices plus a bias vector or each neuron doing some summation, element-wise multiplication, summation, and adding a bias. It's the same thing. Okay. So just as I said, so node receives an input and performs a dot product of vector. So X, this is the input vector, for example, and A, B, and C is the row vector of the W matrix. You just do a dot product. And then the neuron also does the nonlinearity. So once you do the dot product, you do a max of 0 comma that, for example, if you're doing Relu. Okay. But the big motivation for using CNNs or a slightly different type of neurons, a bunch of neurons in CNNs, is that there's going to be a reduction in the number of neurons. Okay, reduction in the number of neurons, these guys. And so if I reduce the number of neurons, it's essentially the same thing as saying I'm going to reduce the number of parameters. Okay, and we'll see how we're going to reduce the number of parameters. we'll reduce the number of parameters, but we'll also exploit some structure of the image type of data set. Okay, so just to I'm going to recap a little bit about uh, uh, so what I drew here is exactly represented in the next slide, where let's talk about the first layer. Then basically these are the inputs. For the first neuron, let's say the topmost neuron, like the first neuron. Remember, the number of neurons is going to be the number of hidden units. So the first neuron will be associated with the first row of the, let's say, the weight matrix W1, and you do a sum, and then apply a nonlinearity. A nonlinearity is also called an activation function, and the output of the neuron is called an activation. Okay, so these are now new terminologies. Just we'll kind of use it here and there. So the output of the neuron, output of the hidden layer, is a hidden layer neuron, or even the final neuron. We're just going to call it activation, and the nonlinearity as an activation function. Okay, and the threshold just means max of 0 comma x. 0 is a threshold or something like that. Okay. So if there is parameters related to activation, you can. Sorry, I apologize. So the threshold is the bias. So these are the weights of the matrix, and threshold is like the coordinate of the bias vector. Okay. So that's and if you look at the connections, we already described how it is. So the number of hidden units is 4, so we get a 4-dimensional vector, and here we get a 2-dimensional vector, and the input is a 3-dimensional vector. Right. Okay, so let's now. So I was just trying to explain a little bit more of the connection between neuron and this representation, because we'll actually try to use this representation to instead of getting bogged down by what exact computation is happening in the neuron. But we know that in each neuron there's going to be a bunch of inputs. There's going to be a dot product, and there's going to be some bias added and a nonlinearity. Okay. So let's now look at. Let me start with motivating CNNs a little bit more. So here's an example data set. It's called the CFAR 10 data set. It's the 10 just means there are 10 classes. And this is basically a data set which has about, I think, 6,000 images per class or something like that. And so there's going to be images. And in the last lecture, we were talking about the type, how is image represented. It's going to be in this data set, it's going to be a 32 cross 32 cross 3 tensor, or an ND array, or essentially 3 matrices on top of each other, maybe one each for one color, and maybe the cell entry representing a number between 0 to 1 or 0 to 255. That's one image. Okay. And so here is a snapshot of the few examples in each of the classes. So this is data set, and this is 10 class data set. So we want to do a 10 class classification. If we were just going to work with feed-forward networks, then we will run into an issue, which is that the first fully connected feed-forward neuron, just the first neuron, so this neuron here, is this neuron, or basically any neuron. So let's say, sorry, this whole thing is a neuron. So it's this neuron. Okay, how many parameters are related to that neuron? Okay, so because we have 32 times 3 is each image. So if you just vectorize the whole image, it's going to be 32 times 3 dimensional vector, because if there's an image, a bunch of numbers in a cuboid shape, but you can just stretch them out, right? Well, you can put the numbers one below the other, and so if there are those many numbers, then there'll be those many parameters in that neuron, okay, and plus one additional bias, and so that's just one neuron, okay. And so what if the images were 1200 times 800? So this would be the number of parameters for one neuron in the first layer. Okay. So we can imagine, you can easily see that if you have 100 neurons, then it's 100 times this number. And if there are more than one layer, third layer, second layer, third layer, and so on, there's going to be many numbers. Okay. Basically, all I'm trying to show is that there is going to be an explosion in the total number of parameters, which basically the dimension of W's and B's that we need to involve. Okay. And so that's one thing that we will help us figure out, which is that we will be able to use less number of parameters, and at the same time we'll hit a second objective, which is to really build our network which takes advantage of the structure of the input data, in this case images, and I'm going to talk about that structure pretty soon. Okay, so now let's look at, so first I'm going to describe the network, and then come back and say how we reduce the number of parameters and how does it take the structure. And it's interspersed in this next in this narration. So let's talk about the architecture. We're going to look at the architecture in the layer point of view, just like. We're going to look at the architecture from layer point of view. So we're going to talk about layers first, and then talk about the neurons. Okay. So in this sense, previously. So in this sense, the new idea here is that each layer will have a width and a depth. Okay. So previously layers only had height. Okay. So if you remember that plot, this is like a height of the layers. If I change the hidden number of circles here from 4 to 400, then that's like a height, right? That just changes the number of hidden neurons. But we'll see that in the layer point of view, we'll also have a width and depth in each layer. Okay. So, and this depth is not related to the neural network depth. So if it's a two-layer neural network, the depth of the network is 2 because of the two-layer neural network. But here, when I say depth, it's the depth of a single layer. Okay. And so let's keep that in mind. So in terms of pictures, what's happening? So this was the feedforward neural network architecture, and we're going to have a we can rearrange. So okay, so what we can do is remember our input image was, let's say we had an image without the depth aspect. The image is going to have a width and a height, right? So the input, actually we can just still represent it as some sort of a square or a rectangle. Let's not worry about the depth as in the 3 colors now. But if it is like that, we can always rearrange these hidden nodes. Even the feedforward network, we can just rearrange them so that they also form a square. So basically, one neuron here is going to be kind of connected to every input coordinate, right? Every input cell. So it's going to be like a pretty dense connection. But you can, so this guy can be rearranged like this. Okay. And the output can be rearranged into a, it's already a vector, so I just have a vector representation. But I'm going to rearrange it in a way where the width and height is going to be 1, and the depth is going to be the number of classes. Okay. I mean, this is not very critical. So all I'm saying is a feedforward network can be arranged as this two-layer network can be arranged as a as if it has a height and width, and even the hidden layer has a height and width. Okay. But still, there's this question of depth. Okay. So the new idea. So what I'm saying is the height and width aspect is not new. I mean, feedforward network, whether it represents it just with height or height and width, it's fine. Now the new idea with CNNs is that you will also have a depth. Okay. So instead of a layer like this, it's going to be a layer like that. Okay. So remember, with we had layers 1, 2, and 3. So input, output layer, and one hidden layer. So we had 3 boxes here essentially. Similarly, we're going to stack things with depth. So these are going to be essentially boxes, for example, in sequence with each other. So that's that's a layer view of CNN. So basically, we'll have boxes. So a box, and we're going to talk about what is the dimensionality of these boxes pretty soon. And there's going to be another box, different sizes potentially, and so on. Okay, so for example, these are 2 layers. Now, again, previously, if you think of from neurons point of view, input had, let's say we are looking at the first layer, input had a dimension of this, and the final output has a dimension of 1 times 1 times 10 classes. Okay. So assuming 2 hidden layers, we're going to have these boxes 1, 2, 3, and 4, right? In 2 hidden layers, we're going to have these 4 guys in the feedforward network representation, we're going to have 4 boxes, okay? And we're going to add depth to each one of them. Okay, so just the 4 boxes, but now I'm adding depth. Okay, now just think of this 4 boxes in the previous slide, but now I have added depth. Okay, so now let's look at the first box. First box is kind of clear what the depth is because I had a 32 cross 32 cross 3. So it was actually a tensor. So there's 3 matrices squished together next to each other. So that's what an image is. And so the box makes sense. So, but what does the box for the intermediate layers mean? Okay, and this one makes sense because this was just a 10 classes, and I said width and height you can just imagine to be one each, and so let's say this is a box. This is fine. This is fine. So we're going to describe what these two are. Okay, but from just looking at this picture, you should be able to see that all we are trying to do is go from this box representation is all it's trying to capture is for example, the input tensor. Okay, so this is the input tensor all the way at the beginning. This is the input tensor to the this is the input tensor to the next layer. This is the input tensor to the next layer, and finally you have an output tensor. Okay, so you can just think of these boxes as some sort of tensors. Although these, I said these are layers, but you can think of these as the shapes of the outputs produced by these intermediate computations. So essentially, a tensor is being produced at each intermediate computation. Okay. So now let's imagine. So of course, when I say a tensor is being produced, the tensor will have elements, just cells. Let's say it's a 3-dimensional tensor. Then it's going to have cells, right? So basically height, width, and depth, and then at each location there's going to be a number, right? You can now imagine that number at each location to be the output of a single neuron. Okay, so each element in this tensor, let's say this tensor, is a number, and that number is produced from a neuron. Remember, a neuron just takes some inputs, has some weights associated with it, does a pointwise multiplication, produces through a nonlinearity a number. Okay, so that's the number here. Okay, but these numbers are arranged in a specific way in this tensor form, and in particular, we're going to look at this particular box is we're going to look at is going to be we'll have a computation corresponding to it, which is the convolutional operation. So it's called a convolutional layer. Okay. And we'll also look at a different layer called a pooling layer. So pooling layer is simple. So let's keep that aside for now. A fully connected layer is, there's also another layer, which is a fully connected layer, which is exactly the same as before. So fully connected layer is what we've already seen. It's just a bunch of neurons which have, which are like in a stacked in a vertical form. So now let's look at so before I get into the neuron description, what is this neuron? How is this neuron computing its output? Let me just look at the layer a little bit more. So let's say our data set is actually CIFAR10. Then here is an example architecture or an example function, okay, model. Input to first, let's have a con layer. Next, let's have a pooling layer. Next, let's have a fully connected layer. And that will produce me the 10 numbers, okay, which is going to be the 10 scores. Okay, so input layer, we already know, it's just the image. Next, the con layer. So neurons are, con layer will also have neurons, just like a feedforward networks layer, but they will produce a tensor as the output. So this layer has to produce different tensor. Remember, I said intermediate outputs are boxes. So let's say, for example, it produced a box of size 32 cross 32 cross 12. Okay, just numbers I arbitrarily chose for now. So the con layer produced a box. Okay. Now the pool layer is another layer. It also should take a box as an input and produce the box, which is the previous layer's output. And take the box and produce another box. Okay. So let's say the pool produces a box which is 16 times 16 times 12. Okay. So what does pool do? I'll explain the pool layer here itself. Pool layer's objective is to downsample the spatial dimensions. So if I get a box, it has a depth. Depth is fine, because the depth was 12. Let's keep the depth the same. Let's not worry about the depth. But it's just going to change the height and width. Okay. And this is just for computation efficiency reasons. So what you do is you have a maybe 32 cross 32 numbers. Now you want to change that to a matrix which has only 16 times 16 numbers. Okay. So how are you going to do that? You can see some sort of averaging of numbers, or that's one way to do it. Okay. You can average out numbers so that maybe you can average all these numbers to get one number uh, uh, here, and you can average these guys to get one number here, average these guys to get one number here, and so on. So that's some sort of downsampling, and we're going to look at it pretty soon. Okay, let's say we did that and we got a box. Now, if we want to connect this box to a fully connected layer, from the fully connected layer's point of view, the box doesn't really mean anything. Okay, so you can as well, you can think of this, I'm vectorizing it, and I know that this fully connected layer has to produce 10 scores because I have 10 classes. So the input is going to be 16 times 16 times 12, and the output is going to be 10 classes. 10 scores. Okay, so it's like a huge vector here, a huge vector here, and some connections like this. Okay, so that's the fully connected layer, and this is an image of that in terms of boxes. Any questions? Okay. We will see that some layers have parameters and some layers don't. The con layer has parameters, and I'm going to describe the details of con layer pretty soon. Fully connected layers, we already saw the parameters. So let's say the number of neurons. Remember, the number of scores we were producing was 10. So because the fully connected layer is at the end, there's going to be 10 neurons. 10 neurons. Because I only have to produce 10 numbers. And each neuron will be associated with 16 times, how many is that? 12 numbers. Okay, so there's going to be a weight matrix associated with this fully connected layer that's going to be 16 times 16 times 10 number of elements in each row, and there's going to be 10 such rows. Okay, so 10 cross this guy. Okay, so each neuron is associated with a huge number of numbers, 16 times 16 times 10, 16 times 16 times 12, but we only have 10 such rows. Okay, so the parameters associated with these neurons are these weights. Okay, and in the overall bigger picture, we're going to optimize just like what we did for feedforward network. So it's going to be a gradient based strategy. We'll probably not do this in using hands or using NumPy. We'll try to use some package. So that's the example. So that's the layer level. What is still not clear is what's the con layer look like, and what are the neurons, because the con layer is also producing a tensor. As long as I can tell you what is the tensor, so each element in the tensor, how is that produced, then we everything should be a little bit more clear then. Okay, so let's now focus on the con layer. So we are only focusing on one layer now. So we have in the whole architecture, we're not, so in the whole architecture, we're just focusing on the con layer. So there's a question about the previous layer, which is explain how the values we get populated in the fully connected layer. So that was this example. So I didn't want to. So remember, so in the CNN point of view, there's always some box, right? At any location, any level of the layer. So let's say at some, maybe there was some computation happened and some box was produced, box as in a tensor. Now, let's say, so now let's say we are at the fully connected layer part. So in the sense there is this layer takes this box as input and it has to produce this score vector, right? So score vector, I just said it's a 1 cross 1 cross k classes where k is the depth. Okay. Although we don't really need this interpretation, but we just need to produce 10. Okay, let's say k is 10. Okay, so 10 classes, 10 scores. Okay. All I'm saying is the fully connected layer, you can just think of this box as so let's say this box is 16 times 12. How we got it, we're going to look at, because this is an output from the pool layer, we'll look at pool layer to figure this out. But let's say this is the size of the box. Okay. What we're going to do is just vectorize it. So this vector is going to have 16 times 12 times 1. So vectorize it just means, put all the numbers one below the other. Okay. Now on the output side, we have 10 scores that needs to be produced. So 10 scores need to be produced. So there's going to be 10 neurons. So this fully connected layer, you can interpret it as having 10 neurons. Okay. Now let's focus on only the first neuron, this guy. Now this guy has to be connected to, because it's called fully connected, it has to be connected to every element, every node in the pass. So in the input. Okay, so the input is going to be this dimensions, and this neuron is connected to everything in before. Okay, now what is the computation that a fully connected neuron will do? It's some sort of let's say max of 0 comma parameters. Okay, so parameters are a x1 plus b x2 plus all the way to x. So what is 16 times 16 times 12? I don't know. Maybe 9,000. I don't know how to guess it. So let's call it n. So let's say n. Okay, plus some coefficient here, right? So now what are these coefficients? Is what I was trying to interpret. These coefficients, which are related to that neuron, this neuron here. These coefficients are nothing but the elements of the matrix A. So this is, let's say this weight matrix collected to the is corresponding to fully connected layer. It's going to be a weight matrix which is going to be 10 cross this number n, where number n is just 16 times 16 times 12. Okay, so A, B, C, and so on. So if you just look at the first row, these are the numbers associated with the first neuron. Okay, so the neuron is what it's doing. It's taking the input tensor, which is 16 times 16 times 12. We're thinking of it as like vectorizing, so it doesn't really matter what shape it is, and taking all of that, getting it in a vector form, and just computing this computation, for which it needs A, B, and C. All I'm saying is that this A, B, and C are just the first row of the weight matrix corresponding to the fully connected layer. Okay. Similarly, the second neuron is going to use the second row of this W matrix. Okay. So fully connected layer is not really doing much. It's just each neuron just is connected to everything else, takes everything before it as an input. For each neuron takes everything before it as an input and produces a single number. Okay. And since we put the fully connected layer at the end, it just produces the scores. Okay, so let's actually go back. So let's look at the con layer. So con layer, remember, now we've zoomed in to just the con layer. So we're not looking at the full neural network. In the con layer, remember, there's an input tensor, and we just need to produce an output tensor, just like in the fully connected case. Okay. So, but to go from an input tensor to an output tensor, we're gonna think of how we're gonna do that, and that's what we're figuring out here. So, going from input to an output, we have to have parameters, right? Just like the fully connected layer had the W matrix as a parameter. W matrix as a parameter. So we will also have parameters in the con layer. Okay. Now, but we're going to arrange these parameters in a specific way. Okay. We're going to arrange these parameters. Parameters are just numbers, right? In the fully connected case, it was a nice matrix, single matrix. But the con layer, we're going to do it in a different way. So we're going to, just like the matrix has a bunch of numbers, those are the parameters corresponding to the fully connected layer. Here we'll have a bunch of parameters. We'll split them up. Okay. We'll split them up into sets of filters. Okay. So let's say we had, hypothetically, let's say we have 100 parameters. Now, all I'm saying is we're gonna, let's say 90 parameters. All I'm saying is I'm gonna split them into sets of size 9, for example. So 10 such sets. So I'm gonna just somehow split those parameters into sets, and each set is, I'll call it as a filter. Okay. So what is a filter by itself? It has a bunch of parameters, right, in it. So it's just a linear function parameterized by a tensor. So a filter, just think of it as a smaller tensor, essentially. Okay. So what is a tensor? Just think of it as for us, it's going to be a 3-dimensional matrix. So just think of, I'm trying to define what the parameters of the CNN layer are. All I'm saying is whatever all the parameters should be, I'm going to split them into sets. Okay. Sets of parameters. Maybe, so let me see. So here's an example, right? Okay, so so let's say I have 270 parameters total. Okay, so I'm gonna split them into parameters of size 27 each. Okay, so I'm gonna make 10 filters, or just think of filters as just names of these collections of parameters. Where the first filter will have 27 numbers, the second filter will have 27 numbers, 10th filter will have 27 numbers, altogether 270 numbers, right? Now, the first filter, these 27 numbers, I'm going to arrange them as a box. So those 27 numbers, I'm going to arrange it as 3 times 3 times 3. Okay, so like a box. So that's total 27 numbers. So that's the example here. So because I arranged it as a box, it'll have three. I'm just using the word pixel, but just think of it as three numbers wide, three numbers height, and three amount of depth. Okay, so and in particular, we're going to look at the con layer, which is interacting with the input, right? In this example, we were doing the con layer was right before the input. The input was a 32 cross 32 cross 3 matrix, and we are now describing the con layer. So you can think of the filter as some sort of a um, function that's operating or convolving with the input image. And for that, let me use this picture to better illustrate it. Let's say this square here, which is 5 cross 5, is the image. Okay, front of the image. Let's just say one matrix of the image. Okay, remember image has three matrices. Just the first matrix. Okay, and I said my filter is 3 cross 3 cross 3. Okay, for example. So let me drop so 3 cross 3 cross 3 means three cross 3 matrices, right? So let me pick the first matrix. Okay, so let's say the first matrix is this guy, 1 0 1 0 1 0 1 0 1. Okay, so those are the 9 numbers in the first filter, first matrix. Okay, what I'm going to do is do this convolve operation. So I'm just trying to describe the convolve or the sliding operation to produce one number. Okay. So what I'm going to do is take these 9 numbers, put it to the top left of the image, do an element-wise multiplication, and sum those numbers out. So just so that happens to be 4 here. Now what I'll do is move these 9 numbers one column to the right, do the same thing, element-wise multiplication with the images uh, numbers, and again produce another number here. Okay, so you can see, so maybe this number is 3. Okay, similarly, I can move the yellow box to 2 steps right. That will hit the edge here and produce some other number 2, and so on. So this is what I mean by sliding the filter onto the input image. Now both the image and the filter have depth, right? The image has 3 layers, and the filter has also a filter depth of 3. Now you can imagine you can imagine sliding or convolving the filter over all the 3 layers simultaneously. It's like uh, a picture. Okay, so all I'm saying is this convolution operation that I'm doing, or so I'm calling it convolution, but all I'm trying to say is that let's say filter is 3 cross 3 cross 3, and the image is 5 cross 5 cross 3. All I'm going to do is take the first matrix of the filter with the first matrix of the image, multiply element-wise, start from top left and keep sliding and doing element-wise multiplication and produce numbers. Okay, sum the numbers, sum the element-wise multiplication numbers and produce a number. Okay, so at the end of this convolution operation, because the filter depth is 3, I'm going to get in this case 3 cross uh, 3 cross 3 output. Okay, because the image size is 5 cross 5 cross 3, and I'm convolving with an image with a filter which is 3 cross 3 cross 3. I'll get a box as the output. So all I want to illustrate here is that if I have just one filter, the 27 numbers, if my input is a tensor, which is 32, in this case 5 cross 5 cross 3, I'm going to produce a tensor, which is going to be a 3 cross 3 cross 3 object. Okay, but to produce these numbers, I use the same filter parameters. Okay, so although the output tensor has, because it's an output tensor, you can think of each one as an output of a neuron. All the neurons, there are these many neurons here, are producing the same sorry okay sorry all the neurons are using the same parameter. Okay, so actually I missed an important step, which is that I do a convolve of filters first layer with the image first layer, filter second layer with the image second layer, filters third layer with the image third layer. Okay, I do these convolutions, I get these numbers, I get a 3 cross 3 cross 3. What I'm going to do is further add, okay, further add and squish the dimension, which is the depth dimension of this filter. So so of this intermediate output, and finally I'll get a 3 cross 3 matrix. Okay, in this case. So all I'm saying is that if I multiply the filter at the top left, there are 3 matrices essentially. Multiply all of them element wise, unsum them, and then you ultimately get one number. So at the end of the day, you get 3 cross 3 numbers. So squash how add the numbers. So if there, add these numbers like this. So if there'll be 4 here, maybe there's some other number here, some other number here. So if you want to squash the depth, one way to squash the depth is to add up the numbers in the matrices which are one below the other, right? So you can just add them. Okay. So all I'm trying to say is that input image 32 cross 32 cross 3, one filter will produce some matrix essentially, because there's not going to be depth, we'll squash it. But the interesting thing is all these outputs, okay, are determined by the same parameters. Whatever be the dimension, it doesn't have to be 3 cross 3 cross 3, but it could be like 16 cross 16 cross something if you want, 16 cross 16 cross 16 cross 16 for example. But all these numbers, because they're on the output side, all these numbers are produced by the same 27 numbers. So there's some weight sharing going on. Okay. So let's notice a few things first. I hope the squashing is clear. So let's notice a couple of things. First is that filters are small. I mean, I was giving an example, which is filter height and width are just 3 and 3. Okay. Filter depth should be the same as the input tensor depth. If the input image, if the input is image, if the convolution layer is at the first layer, then image has depth of 3, then the filter has to have a depth of 3. But if you're doing a con layer at some other location, it's the 5th layer in the neural network, then the depth of the filter should be the same as the input tensor's depth. Okay. Now, as we slide this filter on this tensor, we produce essentially what is a 2D activation map. So that's what this is called. Okay, I mean, it's the 2D because it's a matrix. Remember, we squashed it for a single filter, and it's an activation map because it's we'll interpret this as the output of a neuron. You can also so once we have these numbers, you might as well just apply the nonlinearity here if you want. Okay, we'll talk about. I mean, for my discussion, I don't have to bring in nonlinearity because nonlinearity anyway is element wise. So whether you apply it here or not is not very critical. Okay. So a single filter produced a one matrix. So if I have 10 filters, they'll produce 10 matrices, right? So I can stack those matrices one on top of the other, one matrix per filter. And so I'll get an output tensor whose depth will be just the number of filters. Okay. So, okay, this slide is not talking about that. So it's trying to interpret what filters mean. Filters are essentially some sort of like a edge detector or a color detector and variations like that. Okay, that's what filters essentially mean. How do you keep track of color scale? So we're not keeping track of color scale explicitly. Okay, so input image has already a bunch of numbers. Okay, for example, maybe the image is actually just a plain red image, and the green and the blue channels are 0. So all the second and third matrices are 0. Okay, but once we apply, we'll have, let's say we have a bunch of filters. Let's say we apply the first filter. The filter will have its parameters. We'll apply the first filter by sliding it over the input image. It'll produce a 2D activation map. One filter, one for 2D activation map at the output. We have 10 filters, 10 2D activation maps. But these filters don't have to. I mean, you can interpret the filters. For example, some filters can detect edges, some filters can detect colors, and so on. Okay. But at the end of the day, we are just producing one matrix from a filter, which is a tensor, and the input, which is a tensor. Okay. So for each filter, there's only one matrix. But because I have 10 filters, let's say 10 or 15 filters, I'll have a 10 or 15 matrices as the output, and I'll stack them together to get a tensor at the output. Okay. So, so as I was saying here, filters just can, if you want to interpret them, they do this, but at the first layer. But beyond the first layer, interpretation becomes harder. Okay. So now I want to tell you, because I was talking about a single filter, I can talk about how are the neurons themselves connected, arranged, and where is this parameter reduction. And you can already see that because a single filter with maybe 27 parameters can produce 256 numbers, for example, right? So it's just 27, it's the same weights or same parameters producing 27 numbers. Whereas if you think of these as individual neurons in a Feedforward network, each neuron would have its own parameters. Okay? And in fact, its own parameters would be something related to the input size, and so there will be too many parameters. So, so let's talk about these questions. How are they connected and arranged? So each neuron is essentially looking at a local spatial region of the input tensor. So although we were talking about the sliding operation, at the end of the day, let's go here. Let's say if you think of this as a neuron, sorry, the colors are all. Let's say if you think of this as a neuron, to compute this guy, I only needed this much of the input, right? So if you think of that whole green box as a huge image, this neuron is only looking at a small part of the image, okay? So in the sense that this neuron's computation only depends on a small part of the input tensor, okay? So that's what I mean by each neuron, or essentially each output is only looking at a local spatial region of the input, okay? And the spatial extent you can just call it a receptive field, okay? Like it's like an eye. That neuron is only looking at a small part of the input tensor, and if it's the image, only a small part of the image. And depth is the same as input depth. We just discussed that. So in terms of pictures, right? So let's say we have 1, 2, 3, 4, 5. So let's say we have 5 filters. Okay, first in this example. So each filter is going to produce a matrix. Okay, 5. So this produces a matrix, and if I stack those matrices, so this depth is 5. Okay, then I'll get a 5 depth tensor. Okay. But let's focus on this filter, this neuron. Okay, so which means it's specific to a single filter, right? This, for example, this whole matrix is specific to a single filter. So this neuron is going to be looking at only a part of the input image. Okay, so the number of parameters is fixed because the filter is is produced by the same filter. Now all the other neurons, all the other outputs in that layer or in that layer of the output tensor, they're all from the same filter, which means that all those neurons are sharing the same parameters, okay, which is 27 in number and maybe one bias parameter. Okay. Yeah. And now the second point is that the second neuron, so it's not in the same matrix, so it's produced by a different filter. This filter is also looking at the same spatial region. Okay, that's why it's one behind the other. Okay, so each neuron in this image at least belongs to a different filter, and all the neurons in the same slice. Remember, the slice is like a matrix slice, one slice 2D activation map per filter. They all share the same weights. Okay, so if you go back to the layer point of view, the output tensor just depends on the layer depth. Okay, which is the number of filters. So because the number of filters I said here is 5 filters, the depth of this output tensor is 5. Okay, and it also depends on the stride. So now, so depth is fixed. The depth is this number of filters. Now let's talk about what is the width and height of the output tensor. Now width and height of the output tensor depend on how you're moving each filter. Let's now forget about multiple filters, just one filter, let's say. How is that filter moving across the face of that input tensor? Okay, let's say it's the input image, then how is it moving across the input image? Okay, so that's captured using the stride idea and the zero padding aspect. The stride just means that, okay, I was at the top left. Okay, okay, actually there's a picture right after. So yeah, let's look at stride and zero padding idea on this picture. So there's a 3x3 filter. Input is a 5x5 image. If I stride one step to the right and one more step to the right, and then once I got 3 numbers, these 3 numbers, I do one step below to the left, and then next this guy, and then again to the right, I get these 3 guys, and then the last stride is from the bottom right. 2 more, stride one step to the right, and then one more step to the right. You get these 3 numbers. Okay, so that's stride. That's one stride of 1. Okay. And because I'm not moving beyond the input tensor, zero padding is 0. Okay, because of that, those two pretty much virtually determine what is the size of my output tensor. Okay, the size of the width and height of my output tensor. Okay, so in this case, because stride is 1 and zero padding is 0, it's 3x3. Okay. If I change the stride number, or if I add additional, zero padding just means add additional zeros to the input matrix, like add additional rows and columns to input tensor, so it looks bigger. Okay, and of course, what numbers will you fill there? Just put zeros there. Okay, So that's how we determine the size and the height, width, and depth of the output tensor. Okay. So what is so now let me come back to that idea of reduction in number of parameters. Basically, each filter is looking at uh, uh, each filter, essentially the weights, because they're being reused by, let's say, think of this guy, this particular filter. All these neurons are using the same filter weights. And remember, each neuron is looking at a particular region. So let's say those filter weights were useful for some region, let's say to detect an edge. Okay. The same filter weights can be used to detect an edge all over the image. Okay. So which means that if a filter is useful for one region, it's useful for other regions. And that intuition is only, makes most sense for images. Okay. So that's why we are sharing the filter weights across all the neurons essentially in the output tensor. Okay. So that's what I mean. So this neuron here will also use the same weights and bias parameters as this neuron here, assuming both of them are on that green matrix. Okay. So that essentially, gives, solves this issue of how are you reducing the parameters. So basically, if the number of filters is m, and each filter, let's say, is 3x3 filter, let's say the input is at the image is the image itself, then its depth is 3. And so we'll have these many numbers for the filter, the tensor, and one for bias. So m times this is the number of parameters of the con layer. Okay, so if the m, so this is the number of parameters of the con layer. Now we just compared it to the number of parameters you would need if you had a fully connected layer. That would be vectorizing the input image, which would be 32 times 32 times 3, and then how many neurons you want in the output. Okay, so here's a picture of um, so this is the AlexNet, which is the 2012 CNN, which has a very intuitive form. So it had the first layers is a con layer. It had filters which were 11 cross 11 cross 3. These days people use much smaller filters like the 3 cross 3 cross 3 size I mentioned. 3 is because we are at the first layer. And they chose M, which is the number of filters, to be 96. Okay, so here's a bunch of those. Filters, and because they have depth of 3, you can actually visualize them by thinking of them as images. So you can see like some of them are detecting certain patterns, some of them are detecting colors here and there, and so on. Okay, so that's an example of how the filters look like. I'm going to skip this example. It's exactly explaining try to look at this back home to see that what I said about how the output tensor is computed from an input tensor with a zero padding makes sense. Okay, so here there are two filters. That's why there are two depth outputs and so on. Okay. And you can also try it out at this link. So let me actually stop with that, because that was actually the most important part of the CNN. The pool layer is just some downsampling. I'm going to introduce that because next class we're going to continue to look at CNNs, but mostly in terms of debugging CNNs and so on. So I'm going to explain the pool layer. That's the only thing left, because we discussed the fully connected layer, we've discussed the con layer, and input layer was just the input tensor. We know how the images are represented. And if you want to play with a CNN, there's a CNN notebook also that's shared. So you can run through the, I think it's based on PyTorch. So try to install PyTorch, go to pytorch.org, and there are links in the course page on how to do that. So that you have played around with CNNs the next time you come to the class. Okay, so I'm not skipping this, so I'm gonna start this from here and go to the next week's lecture next week. Okay. So yeah, that's a small part. So in summary, we looked at today we looked at feedforward neural networks. So they're really just a bunch of linear transformations intermediated by nonlinearities or activation functions. And then we also saw this layer point of view for feedforward networks extended to CNNs, except that the CNN layer is a little bit special. It uses less number of parameters to produce tensors instead of flat matrices or just vectors at the output. Okay, and there are some specific properties that it's exploiting. One is that if a feature edge is important, that I can detect an edge in one region, I can also detect another edge in another region. Or in other words, if there's a cat in the picture, if the cat is at the top right or the bottom left, it doesn't matter. We should still detect a gap. So there's some translation invariance that is being exploited um, in this architecture. And there's also, so that's what spatial invariance means. Locality is that if this is all about each filter is just looking at a small region. So a small region can detect something, can tell me something about the image itself. Okay. So let's continue next class. And if you have questions, do post it on our Slack channel. And there's a question. Let me finish this question, and then all of you can leave. Is that why do we do padding? So padding is just so just like striding and padding are two ways to for us to control the size of the output tensor. And padding can also be useful. For example, if you think that there's a region like there are regions in the corners of the image or the previous tensor that are important, you want your filter to move a little bit, to the center of that pattern that you're trying to detect. Okay, so if you don't put padding, you're not able to move move the filter all the way to slide over the image. So it's just you make the image a little bit bigger so that you can try to detect all patterns, whether the edges are almost at the edge or not. Okay, thank you so much. So I'll see you guys next week. Assignment 1 is out, so it's mostly dependent on the notebooks that I've been showing in the class. So if you're not able to access that, post your questions on Slack, and definitely discuss with each other. And if you post it on Slack, other people in the class can respond. Okay, so, and I can also respond. Okay, so that's it for today. Thank you so much.